thanks, you're right.
You'll figure it out, it's not that hard. I was gonna say, if they want something else from you, they'll ask you, you know, what are you gonna? It's just such a formality, so I can't imagine they really need all
I don't
that.
think it's the first time.
Yeah, if I'm not back up here, I.
Yeah,
probably
it
will.
is,
If I'm
because
not,
they used to
just
pay
take
us
it off
differently,
away
but
and just-
at least this time they'll take taxes out, in the past they haven't, and then you had to account for that yourself, you know, like. Yeah. Hi, how are you? Good morning.
I'm M04 Espinoza, and so today I'm going to talk about congruency. Next time we meet, I'm going to talk about similarity.
Okay.
And I'm going to pass the sign-in sheet. So who teaches congruency and similarity
What's the question? Who teaches it?
congruency?
It comes up in our 8th grade curriculum now under the new Common Core when we're discussing rotations, reflections, transformations. Yeah, there are some transformations the state emphasizes that maintain congruence, and other transformations that only maintain similarity.
Okay. Yeah, so I'm going to talk about the, I don't want to say the usual, well, yeah, like the usual presentation of congruency, like the conditions, ASA, SA, AS, and so on, and then I'm going to link it with the motions.
Transformation.
Okay. So I'm going to start with the notation so that everybody has the same notation. Then I'm going to talk about really transformations very briefly. We're going to do then a worksheet, and then I continue, and then another worksheet. Okay. So let me start with notation. I'm guessing everybody uses this notation, but anyway. So these rows, rectangle with vertex. So this angle is going to be denoted by this symbol. Usually this will have a direction, since A is in this segment, and C is in this segment, this will have this direction, right? It will be negative because it's clockwise, and this would be a negative, well, no, it would be, no, yes, it's negative, and then it will be positive because it's going counterclockwise direction, but we are not going to care about directions, so only absolute values. So I'm going to denote this. This will denote either of these signs. Okay. So we're going to say that two angles are congruent. They measure the same distance. And bisects an angle illustrates the angle. So use this notation. We're gonna see, so the line bisects the angle. in this notation means that this angle BD is congruent with the angle this. By the way, this means, I forget to mention this, this symbol means this angle are congruent. Equation. This symbol denotes the segment from A to B. And two segments are congruent if they have the same length. We're gonna denote it by this. Symbol means this is the triangle with vertices A and B. And the usual definition for congruency in triangles is two triangles are congruent if there is a one-to-one correspondence in the vertices such that corresponding sides and corresponding angles are congruent. We're going to use this one here. So this notation means that the triangle ABC is congruent to the triangle DEF, but it says more than that. So this means that the vertex A corresponds to the vertex B, the vertex B corresponds to E, and C to E. And more than that, it's going to say that the segment AB corresponds to the segment DE, the segment BC with EF, and the angles are also corresponding. So saying this is going to be different to saying this, even though this and this are the same triangle, but the correspondence is different, right? So I'm just gonna write this. So this means that also A goes with D, B goes with E, and C goes with F, and that this segment is congruent with this one, this segment is congruent with EF, and CA is congruent with FD. And the angle ABC, so the angle with vertex B, because B corresponds to E, is congruent with the angle with vertex E over here. Okay. Who is new to the grant? Or everybody was here last year? So you're new, and everybody else was here last year. Okay, so last year somebody talked to you about rigid transformations, right? Rotation, translation, reflections, and so on. Okay, so let me recall what those are. So rigid transformations are basically rotations, translations, and reflections. And actually, any rigid transformation can be written as several reflections, up to 3 reflections. But do you remember what properties, 2 properties, all of these transformations have in common? Exactly, right? So the distance doesn't change, and measure of angles doesn't change, right? So that means that these transformations preserve distance and angles, right? Now here we have a definition of congruency that says that 2 objects, well, 2 triangles are congruent if corresponding sides measure the same and corresponding angles measure the same, right? So we can have another way of defining congruency using rigid transformations, right? Which one? Well, we can say, and this is like more general, we can say that 2 geometric figures are congruent if there is a transformation, rigid transformation, that takes one figure into the other one, right? So let me write this down. So we can say that 2 triangles, well, I'm going to write it in triangles, but this we can define this for every figure, where 2 triangles are congruent if there is a rigid transformation taking one to the other one. Right. Okay, so let's do a worksheet. Now the worksheets I have here, you can all of them are in the wiki page, so you can look at them whenever you want. Now I will ask you to not to look at them before the class. I want them to be surprised, but if you can't help yourselves, well, okay, that's okay. The wiki page, well, the way I get to the wiki page, I do a Google PA STEM wiki, and then it, let me show you. So let me.
Or it will, it may not yet.
Is everybody in no, right? No. You here. Okay, so let me show you very quickly. So if you do a if you write PA STEM wiki, the first link is the web page. And then you can, if you click in Immaculata 2015, then it takes you here. So and there are, you can, these are the you're welcome, the worksheets. Okay, so this first worksheet is, we want to figure out if the given triangles, using only rigid transformations, if they are congruent or not. Right? So what do you think about the triangles in item A? They are? Why?
Reflected over the line.
4, right? So we can notice that if there is a line over here, the distance from here, from B to the line is 1, and so is the distance to B prime. From here to here there are 4 spaces, and here there are 4, and here there are 3 and 3. So this reflection is taking this triangle onto this one. So by the definition, they are congruent, right? What about B? Here, sorry. No, why not?
Because the distance is not the same as a reflected over there.
Exactly right. And rigid transformations preserve distance. So there is no transformation taking this one into this one first, because, well, this distance, since it's not going to change, should be mapped into here. But then clearly this distance is smaller than this and this one, so there is not a rigid transformation taking this into this or vice versa. What about items in C? Yes, yes, you said yes. Why? What transformation takes one into a rotation, right? 90 degrees, either this side, taking this triangle onto this, or 90 degrees on the other direction, taking this one onto this one. Very good. Let me see one more. What about that one? As well, right? Those translation 4 units up takes this one into this one.
So it's a translation, is that a slide too?
Yes, slide. Yes, yes, exactly. Yeah. Yeah, slide or translation. Okay, so let's continue. Okay, so I'm going to go over the conditions for congruency, angle, side, angle, side, and so on. And then, these conditions, side, angle, side, actually in many books it's called a theorem, and that's because it can be proved from just rigid motions. Right, so using the definition of rigid motions, we can see that the one implies the other one. Anyways, so let me start with this theorem. Isosceles triangle theorem. And it says the following. So first, we know an isosceles triangle is a triangle that has 2 sides congruent. two congruent sides, right? Okay, so this theorem says the following. If the triangle ABC happens to have the following property, such that the side AB is congruent to the side AC, right? So if we have a triangle with this property, this side equals to this side, then we can say, we can show that this angle must be equal to this angle. The angle with vertex B must be congruent to the angle with vertex C. Right? We are going to show that this is true using rigid motions. Right? So, do any of you do this in class, like showing that this is true using rigid motions? No? Okay, so any ideas how to do this? So we haven't talked about angle, side angle, or side angle, side, so let's just not use those, right? How would you or we show that this is true using rigid motions? So
If you transform those two sides as a, like, say, reflection,
very good.
then you could show that the bottom, the BC, is the same on both.
Very
You
good.
keep AB and AC the same.
Yes. So the way to do this is exactly with a reflection, and the reflection is this. So we are going to draw the bisector of this angle. Right? So I don't know if this bisector cuts the opposite side in a right angle, or if it's cut it at the middle or not. We are not assuming any of those things. We only know that this is a bisector. Right? So let's call this B. So let AD be a bisector. Well, the bisector of the angle with vertex A. Right? And then we are going to apply the reflection. So reflect over the ray AD. Right? So under this reflection, A remains fixed and D remains fixed because the points on the line don't reflect, right? So A goes to A and D goes to D. They are fixed. Okay, so as you said, this line, when reflected, must lie on this line, right? Perhaps goes here, or here, or here, right? We don't know yet. Well, we know, but not yet, right? So why is this line on this line? Because it bisects the angle, and the reflection preserves angles. So this angle must be preserved on the reflection. So this line is going to make the same angle, its image, with this line. So these angles are the same. So this line is over here. Right? Now, how can we argue that then B must go on top of C? Exactly. Again, because it's a rigid motion, and rigid motions preserve distances. So, because this distance is equal to this distance, the only place then for B to be is at C. Right? So we can eliminate this option, and this option, and we have this. Right? So we know B goes to B prime
right? Then we can say that then this side, this segment, then goes over on this segment because D remains fixed and B we just saw goes to B. So this segment here goes over this segment. Oops. BC. Right? Aha. So there we have an angle here, and we have this line going over this line on this transformation. We have this line going over this line on this transformation. This transformation is rigid, so the measure of this angle here should be the same as the measure of this angle here. Right?
Is that when you say because of the transformation, is that because of the definition?
Because the transformation, the rigid transformations preserve the values of angles. Right? So this reflection is taking this angle into this angle, and because preserves measurements, then it has to be the same, right? So the angle ABC is congruent to the angle ACB, right? And guess what? For free we got the following. So this line BD goes onto DC, right? So this is mapped here, and again it's a rigid transformation, so distances don't change, so that means that this length should be the same as this length. So for free we have that the bisector of, I don't want to say an isosceles triangle because there is not assumption on the base, but we can say that the bisector of a triangle with this property intersects the opposite side half at the half point, right? So it's so cool. So for free we get that the bisector, let me just say it, of an isosceles triangle intersects, well, yeah, the bisector at this angle, right? Intersects the base, okay, at the midpoint. Very good. Okay, so this is how we can use rigid transformations to show that the isosceles triangle theorem is true. Okay. Any questions, suggestions? Yes. I mean free because we weren't looking for that, right? So it was something extra that we found on this, right? It's it was given for free. Yeah, we weren't looking for this, right? So it just happened to appear here. So actually we can say, we have a theorem. This is the theorem. And we can prove it. Here is the proof, somewhere here. Anyways. Okay. Good. So let me go over the conditions. I'm just going to list them. And then we go over worksheets. Right? Okay, so we have 4 conditions. Let me start with the side angle side. Condition. Now, as I mentioned, some books, well, the books I was reading, they have this condition as a theorem, and it can be proved using transformations, right? So you start with the definition that 2 triangles are congruent, and then you show that this happens, right? Using reflections. Okay. So the condition says the following. If two sides and the angle included between these sides are congruent, to two sides and the included angle of a second triangle, then these triangles must be congruent, or are congruent. So if we have two triangles having two sides congruent and the included angle congruent as well, then there is no other option for the last side but to actually be congruent and make congruent angles between them, right? They must be congruent. So that's the side angle side. Let me go over angle side angle condition. And this one says the following. So now we are going to have two angles and the included side of the angles, right? So if two angles and the included side of one triangle are congruent, to the corresponding parts of a second triangle, then the two triangles are congruent. Alright, so in a picture we have two triangles having a congruent side and then congruent angles. One here, another one here. Like I don't have to look exactly the same. So if this happens, then the rest of the triangles must be congruent between them. Congruent between them. Well, my picture doesn't look like that, but they must be congruent. Okay, so the last two conditions, the other one is angle side. This is also known as side angle. It doesn't really matter. and says the following. If the triangle ABC and the triangle DEF satisfies the following, first, they have two congruent angles. Angle ABC is congruent to the angle DEF, and the angle BCA is congruent to the angle EFD. And so let me make a picture here. So we have this angle congruent to this angle congruent to this angle, right? And the next is either this side congruent to this one or this side congruent to this one. It doesn't really matter which pair are congruent. So I'm just going to write AC congruent to DF. Could be the other one. So if this happens, then the triangles are congruent. Right. Any comments? Questions? No? Okay. So let me just state the last one, and then we move into the worksheets. Okay. So the last condition, yes, it's very hot, right?
Yeah.
You're okay?
Oh, I'm good, but if you want to turn them on.
No, I'm fine. Well, yes, it's kind of.
Yeah, but it,
This one's
Oh.
always turned
oh, really? Oh, maybe that'll go on, he said.
What? Oh,
Yeah, it is.
that's on. Yeah. Yeah. Oh, okay. So I'll just turn this on.
Well, he just turned it on. Like, when
Yeah.
he came in, there wasn't on at all.
Yeah. Okay. So if it makes too much noise, this one, just let me know. I'm sweating here. Okay. Now the last condition is the side. Thank you. And it basically says that if three sides of a triangle are congruent to three sides of another triangle, then they must be congruent, right? So if the three sides of a triangle are congruent, to the corresponding sides of another triangle, then the triangles are congruent. Right, and as a note, we have that there is no an angle side condition for congruency. So there is not an angle side condition, and also there is not an angle condition. Right? Can you give me an example of two triangles having congruent angles but not being congruent?
Like a 30-60-90 triangle could have another 30-60-90, but the sides could be different.
Exactly, right? Or equilateral triangle with sides 1 and another one with sides 2. All of them very good. And for the angle side condition, let me just make a picture. I'm going to show you two triangles that have one angle and two sides congruent, but they are not congruent, right? So let me take A, B, do this, and then just gonna draw a circle with a length a little bit greater than this length, and then this segment measures the same as this segment, right? Because this is a circle, this is the radius. So here we have an example of there are going to be an angle side that doesn't work. Exactly. Sorry. And then we have this. So I'm just copying this picture, but now I'm going to use this side here. So this angle is congruent to this angle. This side is congruent to this side, and this side is congruent to this side, right? So they satisfy the angle side, but they are not congruent. So there is not an angle side condition. Okay, so ready for the worksheets? Okay. Okay. Okay, so we have plenty of time. Again, you can access these worksheets, you can print them. I thought it was just easier to have them in the wiki page. And
Can you make it brighter?
it's getting there.
Oh,
Yeah,
oh, it's
yeah.
bright. Oh,
I just
sorry.
turned it on. Don't worry. Yes.
There we go.
Yes.
Thank you.
Yeah. So item A, it says which of the following triangles are congruent and why? What condition can be used to determine which ones are congruent? It's not straightforward. You'll see there is a trick over here. Can we eliminate one between them? Which one? We can eliminate the top one because this hypotenuse is 2 and the 2 here, wait, no, we cannot eliminate this one. The left one, right? Because this hypotenuse is going to measure more than 2. So it seems like these two are congruent, right? And so what would be the condition that says, yes, these two are congruent? Side angle. But wait, side angle side. Where is side angle side? Side angle side. The angle must be in between, right? so we will have to show that this angle here is equal to this one here, right? We don't want to show it, right? So there should be another way, another condition that helps us here.
Well, if two sides are the same, the third side has to be.
Well, in this case, because this is a right triangle, we can very easily use Pythagorean theorem to determine the value of these ones, right? And the same formula will hold for both, and both have 1 and 2 as a hypotenuse and 1 as the other side. So this side has to be equal to this side, right? So the condition that helps here is side, 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 right?
But,
Yes.
okay, I see what you're saying. If that were not a right triangle, would you be able, because technically
Ah.
it's like angle side, side.
No, that's why I made it a right triangle, yes.
Okay, so it only works because of that.
Yeah.
All right. It works.
Because it's a right triangle, yes. Oops. Sorry. Right. Yeah, we had one like this here, right? This. Okay, good. So what about the next one? Sorry, here I missed. I meant to write a 3 over here.
Oh.
Right, so there should be a 3 here. So which ones are congruent and why? Hmm?
The bottom two.
Yeah.
The bottom 2 because of condition angle side angle, right? Angle side angle. So these angles are equal, this side is equal, and then this angle is equal, right? What about
He said he forgot it.
C?
First one and the last one.
Yeah, that's too
The
big.
first one, exactly right. Side, side, side. Good. E, E, F, E, F. Okay. So now let's remove the numbers. So what about in question 2? So in this figure, we assume that this side, this segment is congruent to this segment is congruent to this segment, and we want to show that this triangle here on the left is congruent to this triangle here on the right. So are they congruent, and why?
Side angle side.
Side, angle, side, and what are we using? I'm guessing exactly right, the vertical condition. So if we have two straight lines, opposite angles are congruent.
Eighth graders cannot remember that one. Cannot remember the word.
Really?
I've tried everything. They're kissing, the bees are kissing, they're bees, like they're
Yeah. No? Oh. Anyway, so this is it, right? Two lines intersecting, straight lines, opposite side, opposite angles are congruent. Very good. So that's side, angle, side, right? Yes.
Just so I know, on the wiki space,
Yeah.
whatever the link is called, these papers are there and the answers are there too.
No, just the questions. Yeah, I mean, I could write the answers if you want. And, yeah. It's, now let's haven't talked about this yet. Well, here let's suppose that we want to write the answer, right? So I'm gonna say triangle CAE is congruent to triangle, so you fill in the blanks. What do we write? So I'm talking about the same triangle. So how do we write? D B E, right? So the vertices must correspond, right? Very good. So we have C with D, A with B, and E with E. So okay, good. Okay, so in 3, we have the following figure. And so we know in this figure, we know that this angle here, CAD, is congruent to the angle here, BDA. And the angle here, ADC, is congruent to the angle here, DAB. So what condition tell us, which condition tells us that these two are congruent?
Angle, side angle.
Angle, side angle, right? Because this angle here is congruent to this angle here. They have the same side. They share this line, and then this angle here is congruent to this angle. All right. So in a picture, so we have. So they have two congruent triangles and a congruent side in between. All right. Cool. Okay. What about the next one? So we have two isosceles triangles. For both, the base is AB. So this is the base of the triangles, and they are the triangle ACB and ADB. Now we want to show, we have to say, what condition give us the congruency between the triangle ADC, so this one on the left, and the one on the right, BDC. So we need to show that they are congruent. So how do we argue that they are? We don't know. It's easier if you do a picture and start on market side, right? Really good. Let me see what. So we have. So we have this side is equal to this side is equal to this side, and well, they share this one. So side implies that this triangle is congruent to this one, right? Cool. Okay, so two more. And I have another worksheet after this one, and it's different. But okay, so in the next figure, the segment AD is congruent to the segment BC, and we want to show that this triangle is congruent to this one, and why? Side angle or angle side, right? So what side are you talking about? Okay, so this side is equal to this side, and then this angle is equal to this angle, and then by the vertical one, this angle is equal to this angle. Cool. Okay, now I'm going to give you, let's say, 2 minutes to work this one out. Right. Good.
I forgot my calculator.
You can borrow this one.
That's okay. I've been having a good time estimating the value of the square root of 13 using my other one. So I want to see how close I am.
Do you know how to take square roots?
I never learned that algorithm.
I can show you
But
later if
I
you want.
estimated it, and I knew it was somewhere around 3.60 something. So
Our
let's
book
see how
would
close
leave it
I
as
was.
2 times the square root of 13.
Yeah.
Like they would.
Yeah,
So
yeah.
you could leave it, Ruth.
Yeah.
Well, I did have it right there. It was.
We left our answers in pi
And
yesterday.
then I estimated it. Hold on. I have to put the square root symbol in first.
So
Yeah.
when you were doing the, like, showing us
See, look how
earlier
close
with
I am.
transformations,
Mhm.
like why the triangle was isosceles and
Yeah.
so on, you could do that also with the Pythagorean theorem. Like, isn't there another way to do it? Also,
Well, but you will need to show that the bisector intersects the base and a 90-degree angle.
right.
So if you know that, then you can use
Okay,
others.
so is that
other
a valid
things.
proof though? If you say you bisect it?
Well, if you have proof before that it's gonna bisect it in a 90-degree angles, then
Okay.
it will be yes.
I'm
but,
just like having these memories from
Good.
I was
geometry,
right.
10th grade, and I'm thinking,
yeah,
but I'm thinking I don't remember doing it that. Like I remember somehow doing it another way, and I was just kind of foggy on it.
Yeah,
it
no,
was a
no.
long time ago.
So yeah, so as long as you know already that it was gonna be it's
Okay.
going to be 90-degree angle, then you can use.
Okay.
Yes. So yeah, you got yeah.
Yeah, I got the answer even before. Well, it
Yes,
was an easy one
good.
to take the square root of.
Good.
That answer. But now, taking the square root of a number, do you know that algorithm?
Yeah, yeah. I'll show you
Difficult
later.
to do?
No, it's not difficult. It's just
I never learned that.
No, I never did either.
I know
really.
it exists, but
Yeah.
nobody ever taught me.
Yeah,
I never
because there
bothered
was
to
a
look.
time there weren't calculators. Right?
exactly. I learned without
Yeah.
calculators.
He's too young though to have done that.
No,
but
I'm not.
it.
I look younger.
Really?
yeah.
Yeah, I was gonna say. Come on.
No. So it's so everybody got 7.2, right?
Yeah.
Good. So sometimes, so no, I saw you 7. Okay. So
You made the
you found this,
error.
and then we wanted this. So yes. So
Yep, everybody does that.
I was gonna say nobody did that. Oh. Anyways, okay. So let me show you the last worksheet, and it's gonna be slightly different because we want then to do kind of proofs.
Okay.
Now we want to use side angle sine to show that if a triangle has the property that it has two congruent sides, then it has two congruent angles. Does this look familiar to you? Is the one we just proved with transformations, right?
Okay.
Well, now let's do it using side angles,
Okay.
right?
This will be easier.
So just gonna make that figure that doesn't fit our perception of that these two are equal. All right. So we have like 15 minutes, right? So okay, so I'll give you okay. So how do we do it?
We're done already?
No. How do we do
Oh, I
it?
was gonna
Sorry.
How do we do it?
How do we?
Oh, I'm
15
sorry.
minutes, so come on.
Okay.
Now look,
That's what he said.
all these conditions. No. All of these conditions to use condition SAS, SSS, and all of them says if we have one triangle satisfying this and another triangle satisfying this, then these two are congruent, right? Now here we have just one triangle, and we want to apply SAS to prove something on this one triangle. How can we do that?
Make a formal proof.
Kind of, yeah. We
So
can.
do we have to bisect it?
No bisectors.
Without reflecting, right?
Yeah.
Well, you know that BC is congruent to its. Oh, wait, no.
You're in the right path. So we need at least another triangle, right?
Right, Ruth, you're right, because BC is congruent to CB.
Yeah.
Yes. Yeah. So we want to show this angle equals to this angle, right?
Okay, so, alright.
So let me
But I know that if two sides.
let me give you a hint.
Right.
Let me give you a hint. What if we are able to prove that these two are congruent? right? So the triangle ABC congruent to the triangle ACB.
And we need side, angle, side.
So first question, does every triangle satisfies this? No, right? Let me show you an example of, because you can say, oh, come on, this triangle and this triangle are the same. Well, they are not the same per se, because look, the trick here is the notation. But look, suppose we have a triangle with 30 degrees here, 40 degrees here, A, B, C. The triangle ABC is the same as the triangle ACB, but they are not congruent. Not like this, because this congruency would mean that the vertex A goes to A, the vertex B goes to C, the vector C goes to B, and then this angle goes to this angle, but they are different, right? So the triangle ABC is not congruent to the triangle ACB.
Can you use the definition of an isosceles triangle?
Well, the definition is that these sides are equal, right? We don't know nothing about the angles.
Doesn't it say that if the sides on an isosceles triangle, the sides are here and then the angles are
But that's the theorem. The theorem we prove that's a consequence of being isosceles, that these two are equal.
But we don't know.
But that's what we want to prove. But you see, look, if we can prove that this is true, then let me just make a picture of the same triangle here. I'm just going to flip it, right? If we can prove that the triangle ABC is congruent to the triangle ACB, then that means that this angle corresponds to this angle, right? And that this angle corresponds to this angle, right? So we are saying, look, this angle corresponds to this one, and this one corresponds to this one. They should be the same.
Know what she said already, though, that the sides across from the angles across from corresponding sides. We don't know that yet. We can't say that.
That like this angle is equal to this angle? No.
No, that because the sides are the same, the angles across from them are also the same, but we can't use that.
No.
We can't use that.
No, not yet.
Okay.
So because the corresponding angles of those two triangles are congruent, then
Right. But we have to prove that they are.
but we haven't done that
Yeah.
yet. So you-
But it's, if we prove this, then okay. So if we prove this, everybody agrees that then we have the equation. Well, that these two are congruent, right? Because this angle corresponds to this one, and so they must be the same. So how do we prove that this is true?
Oh. Because the A is.
Exactly, right? So this side AB is equal to side AC.
Oh, we don't make it harder.
Side AC is equal to side AB, and this is the same angle, right? So side angle side implies these two triangles, this notation, are congruent. So this angle is equal to this angle.
If he had labeled it differently, like labeled that one differently, then the A's may not have necessarily been.
Well, could you have said some arrangement where an angle besides A was in the same place? So if you said C.
But then we will have something like, so that case works because these two angles are equal. A different arrangement may not work, right? So we want A to be the fixed one, because we know that both triangles have the same angle here.
But the angle A is the same.
Exactly. Right? But this is not true, right?
In that one. But we didn't have an angle.
No, because these angles are different here, right? So all of this is that because well, it happens they're going to be equal, right? Then you can imagine then how to solve the next one. Now this is going in the opposite direction. Now we are assuming that we have a triangle that has two congruent angles here. Now we want to show that these sides are congruent. We want to use angle, side, angle.
And then that would show.
So it's the same trick, you see? If we show the triangle ABC is congruent to ACB, right? So this angle is equal to this angle. This angle here is equal to this angle here because that's the hypothesis. And this side is congruent to this side. So by angle side angle, this triangle is congruent to this triangle.
But in this time, you're telling us ahead of time that they are congruent. We're not
No.
proving that they are congruent. We're proving that the sides are the same.
Are congruent.
Right.
So we don't have, now it's the opposite. So in the previous one, we know the sides were congruent.
Right. So we're
Now,
doing, okay.
yeah, we're doing the reciprocal. Cool. Okay. Two more. Yes. Okay. So this one. Let ABC be the triangle with vertices 0, 0, 3, 1, and 1, 2. And let DEF be the triangle with vertices 0, 0, and then 3 minus the square root of 3 over 2, comma, 1 plus 3 times the square root of 3 over 2, and the other one, right? So how would you show that these triangles are or are not congruent? So plotting them makes no sense because, well, we will have to plot.
Do side, side, side.
Very good, right? So we cannot plot. Finding angles, it would be difficult. So we can use the distance formula. And if all the sides match, if we have pairs of congruent sides, then they will be congruent, right? Any guesses?
It is.
It is. I took the triangle ABC and I rotated 30 degrees, and then I found the other vertices.
We teach the kids to just look at what you did to it. Like to, if you took
yes.
3 and subtracted the square root of 3 over 2, and you took 1 and added the square root of 3 times 3, and then you did the same, like on the other one,
Yeah.
it's the same.
Well, we have a two.
Right.
Yeah. But, so yeah, but it's like a rotation of. I did it 30 degrees, I believe. So. Right. Okay. So let me finish with one last problem here. Okay, so we have like 2 minutes, right? So suppose that this is a river. And we want to know the length across the river, right? And we have a fence if you want here. Now the problem is that we are not able to cross on the other side. So we want to use congruent triangles to measure the distance across the river. How would you do that? We are on this side. And we can grab rocks and we can measure distances on this side, right? But that will be next time we see each other, because that's going to be similar triangles. Yes. That will be similar triangles. No, not with congruent triangles. So the hint is You remember problem number 5 or 6 from worksheet number 2? Think about that configuration. Or, well, we can perhaps think on that configuration on the other, right? Any ideas?
So is that the fence on the right?
It's a fence or something that
No, I
we
mean
have a
the
reference.
triangle on the bottom that you made.
Ah.
Is that the-
No, I'm just making a picture. So, but yeah, you can use the fence, or you can use the tree for. Right. So since we have very few minutes left, let me give you the idea how to do it. So we have, let's say, I'm going to use the tree. Right, the tree is on the other side of the river, right on the edge of the river. So we can place a rock on this side, just directly from the tree. Right. So here's the rock. Right. So then we can place another object on this direction, another rock, right? And we know this will make a 90-degree angle, right? So we just walk this, and we measure rocks, and I don't know, let's say 7 meters, right? And then we're going to walk here on this direction, and we're going to place another rock right when we have the tree on our side, on this line. So we start walking, and right when we have the tree in our line side, we place the rock.
You could have the tree in line sight shorter up.
Sorry.
Like, come here and look at my picture.
Yes.
Like, you said to stop right, huh?
When you have.
Yeah, but look, if I go down here, I can still see the tree this way. And that's not, like, what do you mean, the tree in my line?
Yes, sorry. Yes, sorry. Let me make this an even number. Okay. And we place, I forgot the other rock, halfway, another rock.
okay.
And then we want these three line up. So we have this rock, the tree, in our side, line side.
Rock you just add as the midpoint?
At the midpoint. So this is 4 meters. And then these two are going to be congruent. And so whatever this length is, that would be the length of the river. And of course we can measure this and measure this. Right? Whew. Does this make sense? Right? So a very nice application of congruent triangles, right? Measuring the river, and we are on this side. Next time we see each other. Well, we could do it, but we need some reference on either side. So next time we're going to do something similar with similar triangles. In that case, we are allowed to cross on the other side and draw some triangles. Okay, good. So I guess it's almost 9:30. That would be we already proved in 5 that these triangles, if this is equal to this one, these are going to be congruent, right? So we don't need to prove them because we already know they will be congruent. But if that would be side angle, and angle, side angle.
And then if you know that one on the right, if you can measure that right one.
Here. Then
That's
you
what
know.
you were getting at. 'Cause you wanted to know how wide the river was, so you have to count that one.
Exactly.
So
So
if you
whatever.
know they're congruent already, though, you really don't care how far those.
Exactly.
are.
You
You just have to measure that one.
Exactly. Good.